Assalamualaikum and a very good morning to everyone. My name is Azira Hani binti Akasha. My matric number is AN170073. My supervisor is TS Dr. Lam Hong Yin and I am from Department of JTKE Faculty of Engineering Technology. My final year project is titled Development of CanSat Satellite, which is CanSat, On-Board Communication for Data Acquisition and Transmission. The objective for this proposed project is to develop onboard communication hardware embedded in the CanSat transponder, to develop an onboard communication algorithm and programming for data acquisition and transmission to the ground control station, and the last part is to integrate the development of hardware and software solutions and validate the overall system performance. Now, for the background study of this project, we understand that satellites can provide global coverage and persistent communication services for various technological applications. This project focuses on a mimical of a real satellite called CanSat, which is short for CanSat satellite, integrates in a soft drink can and acts as a transponder. Hence, this work focuses on an onboard communication system that transmitted data acquisition from the transponder to the ground station. The three main scopes of the project is the navigational controller that provides a monitoring interface act as control commands and data collections, which revolves around altitude, latitude, longitude, acceleration, temperature, and humidity by using the APM 2.8 flight controller. The second part is the onboard computing system involves a Raspberry Pi as a microcontroller. And the last part is a system that communicates between CanSat and ground control station using a 3DR radio telemetry kit and a GPS module. After taking a consideration of comparing overall literature review, two of the reviews are most relatable to this project that brings close findings into conducting for the methodology. From the first review, the study depicts that the communication system is the main part that sends data from the CanSat to the ground station in real time, as the microprocessor must be able to collect all data from the sensor subsystem. Hence, this comes to a conclusion that the work indicates the effectiveness of data acquisition. The telemetry information should incorporate score-set GPS coordinates, measured temperature, humidity, pressure, and altitude for every seconds during descent in real time to the ground control station. From another point of view review, the study pointed out that telemetry processing and data storage are vital to fulfilling the primary mission, as it is related to the downlink to the ground station, as CubeSat provides flight software FSW patch and load and fault protection for the flight software embedded in the OBDH system, which is the onboard data handling. The work shows an efficient way of data storage as part of the flight software design. Study found that the flight software embedded in the onboard data handling subsystem in the transponder served as the brain of a satellite. For the methodology part of this project, we focus on the flight software design that shows overall integration between hardware and software. The design of the flight software considering requirements in Table 1, the telemetry data from the sensors will be transmitted to the microcontroller unit. Such data will be stored on the memory storage and transmit to the ground station via radio telemetry transceiver. Based on Figure 1, the score-set hardware development is designed according to the architecture of the block diagram. We can see that the camera, sensor, SD card, and transceiver is being connected to the Raspberry Pi 0W, and the GPS is connected to the Arduino Pilot APM 2.8, whereas the Arduino Pilot APM 2.8 is connected on the Raspberry Pi 0W. For the design shows overall parameters such that the software for Raspberry Pi 0 is to perform data acquisition for telemetry data and to store telemetry data to memory storage card with a timestamp. For the Arduino Pilot APN 2.8 is a flight controller that has parametric color radiometric transformation between observed and environment phase for feature classification. And for the development of environment Python, we use IDLE, which is Integrated Development Environment for Python, and we use C++ language. For the data rate, Raspberry Pi Zero is about 14 megabytes per second, and data rate of its Arduino Pilot is in 64 kbps. The results and discussion shown here is the overall data acquisition transmitted by the onboard communication from the transponder. We can see that in figure 2 shows the interface of mission planner, position and altitude that can be read in this interface. And for the figure 3 is a live visual from Pi camera that connected to the Raspberry Pi. And for the figure 4 shows the raw data of CSV reading of DHT11 sensor and a barometer BMP 180. For the next part is the project demonstration for the onboard communication in flight stage and post-flight stage. First, we see the communication stage. We connected to the transponder via Wi-Fi so that the microcontroller can transmit to the ground station. As we open the terminal, the ground station can read overall sensors in the transponder. Now, Mission Planner is the second user interface at the ground station. Select the correct port to connect the APM 2.8 module in the transponder. So we can see here that the Mavlink is connecting to the ground control station to get the exact data acquisition from the transponder. For the in-flight situation, when enter the command key, the telemetry data is transmitted to the user interface. Here, we can see the readings for temperature and humidity for the DHT11 sensor and another temperature, pressure and altitude reading from the barometer. The data is showing the timestamp too. This command is to activate the Pi camera. Pi camera will record the video and save in the memory storage in Raspberry Pi. Now this is another of the user interface to monitor the Raspberry Pi. This user interface is to monitor the APM 2.8 module in CanSat. Location of the CanSat is shown due to the GPS module embedded in the transponder. Besides that, it also shows health monitor of the APM 2.8 module in CanSat. For the post-flight stage, the video recorded by the Pi camera can be found in the memory storage of the Raspberry Pi. We can see here the visual of from the Pi camera recorded. All the sensor reading is saved as backup for validation in the memory storage of the Raspberry Pi. The file is saved in a CSV format. The telemetry data can be compared with the display in the user interface. This is another of the sensor reading from the barometer. We can see here the data is tally with the readings from the CSV format in Excel. Now, as we conclude, the project task and assignment for the whole period of drafting FYP2 phase has been implemented successfully, such as the performing integration between hardware and software of the prototype payload subsystem. I want to express gratitude to my supervisor, Dr. Lam Hong Yin, for his guidance, encouragement, advice, and full support into completing my duration of final year project. I also would like to acknowledge my CanSat team who helped throughout the deadline submission task for Malaysia Siswasat Competition 2020, although we were amidst in COVID-19 situation. I'm much obliged to my team members for their dedication, teamwork, and cooperation. That is all for my presentation today. Thank you for watching.